In this chapter, we will look at classifying chemical compounds into two broad categories, those that are living and those that are not. As you've learned, compounds can be classified as ionic or covalent.
Developed a system of arranging dots around the symbol of an element to represent an atom's valence electron.
These two categories of compounds are based on how
By valence, we
they
mean
bond.
outer electron.
We're going to look at how compounds can be categorized another way, and that is the two categories organic and inorganic. That's basing things, breaking them down into categories based on whether they come from living things or they're a component of living things, or whether they're not a component of living things. Organic compounds are compounds that are based on living things or come from living things, and they have a high percentage of carbon.
So it has 2 in the inner shell.
So they have a
If you were
high
just to show the outer shell,
percentage
then it
of
would go
carbon,
like this, having 7. This is the Lewis
and that's
diagram.
determined by mass. So they have a high percentage of carbon by mass, and they must also contain hydrogen.
So to define it again, a Lewis diagram describes an atom as it prepares to bond.
Examples of organic compounds are things like sugar, methane, and vitamins. Inorganic compounds are compounds that have little or no carbon.
And it can also sometimes be called an electron dot diagram.
So compounds that have little
to follow when you're trying to draw Lewis diagrams.
or
First of all
no
is to determine
carbon.
the number of valence electrons.
Examples
the
are
number
things
of
like
electrons
water,
in the outer
salt, carbon dioxide, etc. So we're going to make a little classification chart here. At the
And then
top
the second thing that you will
is
do
compounds,
you will write the symbol, and then you will arrange the electrons around.
and
it.
compounds can be broken down into two
You'll
different
arrange
broad
electrons as
categories.
dots
Those that are
around
non-living, so inorganic,
the symbol.
and coming from living things, organic.
How this would look for chlorine, for example, if you figure out.
Well, you know what,
chlorine
actually I'm
has
going
7 valence
Sorry, I'm going to do this the other way around, so
you
just
would
erase
draw,
this.
the
I'm going to put
symbol
organic
for
over
chlorine
here,
and
so I'm looking at the way
arrange
the arrows
7
go
dots
beneath.
around it
So
as
organic, inorganic. Because all organic
When you're
compounds
considering bonding
are
to
covalent,
learn what the octet rule is, and the octet rule really
whereas
just means
inorganic
that
compounds
the
can be
electrons,
either
the
covalent
elements would
or
like to have,
ionic.
a full octet. So they want their outer shell to be full. So when bonding,
In section 8.1, we're looking specifically at inorganic
each atom
compounds.
has a tendency
So we'll look at the two categories that fall underneath this.
to fill its outer shell.
Inorganic molecular compounds have little or no carbon.
And when it does that, it will match the nearest noble gas. To match
They're molecular,
Nearest.
so they have covalent bonds.
noble,
And there aren't really a lot of these.
that's called the octet
Most
rule.
inorganic compounds are ionic.
Here's
So
an
this means
example
that they
of
are
using
made up of a
Lewis
metal and a
diagrams to show
nonmetal.
bonding
And
in a water
these are all the ones
molecule.
that you've studied
So
so
in a
far.
combination of hydrogen and
So
oxygen.
inorganic
We
ionic
have
compounds can be broken down into
that
3
hydrogen
more
shown here, and they're
categories:
using an
acids,
S
bases,
to
and
symbolize
salts.
this electron
So we're
just
going
so
to
that we
look
can distinguish
individually at
them
which
from
each of
oxygen.
those,
Hydrogen
which
just has 1
what makes each of those
in
what
its
they
valence
are.
shell, and oxygen has 6.
So an acid
So when you're
is
going
something
to
that
combine them,
releases
then you will
hydrogen
end up
ions
with both of them
in
having
solution.
full outer shells,
So you know
while
that
hydrogen each
ionic
having
compounds,
2.
when you put them into a solution,
It would
will break
have
down into
2
their
to have its outer shell full. It
ions.
only has the
So
1
it'll
shell,
release H
and
plus
oxygen
ions
now having 8.
in solution.
So when you're doing Lewis diagrams with molecules,
Acids have a sour
then there's
taste.
a third step to show the bonding.
Acids conduct an electric current, just like all
Just
inorganic
like they've
or
done here for
ionic
the
compounds
water
do.
molecule.
So conduct an electric current.
So over the page, all
They
of
react
these
with metals, not with all metals, but with certain
outer
metals
shells, and I'm
to
gonna write
produce
down
hydrogen
each
gas.
valence shells.
So react with certain metals to produce, and hydrogen gas would be H2 gas.
As a result of bonding
And they cause
pairs of
chemical
electrons.
indicators to change color. So I should put cause chemical indicators to change
Lone
color. For
electron
example,
pairs do
if you
not form
put
bonds, and we're
litmus
gonna look at
paper
what that means.
in
So
an
here
acid, it'll
is,
turn red.
Ammonia.
Bases,
And
on the other
ammonia
hand,
has
don't
3
release
bonding pairs.
H plus ions, they
Three
release
pairs that are
hydroxide
involved in
ions.
bonds,
So
and it
release
also has 1 pair of electrons
OH negative
not in a
ions
bond. So
in
those are
solution.
called, oops, I'm going to change this back.
Bases are alkali.
I want it to be a pen. Those are called a bonding pair.
Bases
Or
are
not a
slippery
bonding pair, a lone pair.
and they're bitter.
They are not involved in bonding, so not bonded.
They also conduct an electric current.
Bonding pairs are electrons involved in
Again,
bonds.
just like all ionic compounds.
Sometimes you'll be asked to identify
Over the page, continuing on with
how
bases,
many bonding
they
pairs
do
there
not
are,
react
or
with
how many
metals to
lone
produce a
pairs
hydrogen
there are.
gas.
So ammonia would have 3 bonding pairs.
So do
and
not
1 lone pair.
react with metals.
And for simplicity, to make this even simpler, the bonding pairs of electrons are often replaced with a line. So bonding pairs
To produce
of electrons
H2
often
gas.
replaced by a line.
And
Here's the
like
same
acids,
ammonia
though, they
molecule
cause
again, showing
chemical
each of the bonding
indicators to
pairs
change
with a
color.
line. So this line represents a bonding
So if you
pair.
put litmus paper in a base, it'll turn blue,
We do not
where
do that, though,
in
to the
acid it
lone
turned red.
pair. Still show that as electrons.
Salts are the third
Okay,
category
we're gonna look at Lewis
of
diagrams
ionic
for
inorganic
compounds as
compounds,
well.
and they
And
release
since the
positive
formulas for
and
ionic
negative
compounds
ions
are
other
based
than
on
H plus and
charge,
OH negative.
we seldom rely
So
on these
release
structures.
positive
If we did, then the Lewis
and
diagrams
negative
would show the electron transfer
ions
that can still be shown in a Bohr diagram. So simply show
other
the
than
electron transfer.
H plus and OH negative. So neither of those will be released when you're looking at salts.
That can be
They
shown.
do, though, conduct an electric current.
In a Bohr diagram.
They do not
And there are
react
some
with metals
rules,
to
some
produce
special rules
hydrogen
that you need to
gas.
follow when you're doing these for Lewis diagrams, and those are that you need to have brackets around the symbol, because of course it's going to be an ion. You have to
And they
show
have
the
no
ion charge,
effect on chemical indicators.
and you have to show
So if you
arrows
are using any
Show
chemical
arrows.
indicator, you will not be able to determine
to show
if it
transfer
you will
valence.
it will just not have a change when you put it in a salt. So have no effect on chemical
They're going to be
indicators.
negative as electrons. So here we have the Lewis diagram showing
Okay, we're going to look at the
sodium
concept of
atoms
acidity,
combining with
and we're just
oxygen.
going to scroll down
in
here
an
to this
ionic
table,
bond.
table 4, classifying
the same
solutions as
thing shown
acidic,
with
basic,
Bohr.
or neutral. And we're going to be looking at the ion count to do this.
Both are showing the
So
same thing.
for
At
something
the
to be
bottom,
acidic,
we get the
then there
chemical
must be
formula.
more H plus than there is OH negative. So more
So
hydrogen
that in a
ions than there are
nutshell is
hydroxide.
Lewis diagram.
For something to be
We're
basic, it
gonna
has to
switch
be the
gears
other
a
way
little bit
around.
right now
So
and
the
take a
H
look
plus
at organic
ions have to be
compounds.
less than
I'll
the
open that up.
hydroxide. For something to be neutral, then the hydrogen ions have to equal the hydroxide ions. So therefore acidity
Organic
is really a
chemistry
measure
is the
of how
chemistry of
much the
carbon
relative
compounds.
quantities of H plus and OH there are in a solution. Chemists have a scale to measure acidity, and it's a log scale, and it's called the pH scale, and it goes from 0 to
Organic
14.
compounds
And
always
this is on
contain
page 205, so see
and they
page
also
205
always
of your
contain
textbook, and there's a more
hydrogen. So
complete
contain
scale
carbon
there. But just to
and
put some
hydrogen.
things on,
People
0 to
often forget
14,
about
so
the
right in the
hydrogen.
middle would be 7.
They can
and
also
that is where
contain other
pure
elements,
water
but they definitely have to
would
contain
fall.
both of these. And they're
Water
also
is,
molecular
and
or
I'm just going to draw
covalent
this up
compounds.
here, HOH. That's just another way of writing H2O. And HOH will break down into
Here are some
H plus
examples
and
of
OH
some
negative.
common
So it has
organic
both
compounds, and what I'd like you to notice
H plus
here
and OH
is that
ions,
carbon
but it
and
has
hydrogen
equal
are
numbers.
always
It'll always
present.
break down into 1 H plus and 1 OH.
Carbon
So it'll come out
hydrogen
completely neutral.
always present.
For something to be less than 7, it is an acid.
You can be asked to identify
So
From the
going this
formula,
way on the
if
scale
a compound is organic
is
or
more
not,
acidic,
and you will have to
going
study
this
it
way
to determine if
is more
carbon and
basic,
hydrogen both
so the
are
bases would fall
present.
over here.
So for example,
To put on some
CO2 is
examples,
not organic.
at a pH of 1
It has
is
carbon but
stomach
not
acid,
hydrogen.
so the acid in your
is
stomach has a pH of 1. And
both
at
carbon
about
and
10
hydrogen.
is where we find most soaps.
So what's so special about carbon anyways? Why is it that carbon
And again, on
is the
page
basis
205
for all these
is a more
organic
complete
molecules?
scale with more
Well, carbon
examples
is special
all
because
along
it has
that.
4 valence electrons.
The next thing we're going to look at in 8.1 in this
So it
section
has
is
4
naming
electrons that are
acids.
available for bonding.
So to do this, what you need to
And
do
so it
is
can
look
form
at the
several
formula.
bonds with
And we're going to
itself
create a
and
little
other
flow
bonds.
chart based on the
And
formulas.
can
So you will
form
examine the
several
formula.
bonds.
And so here are some
with
examples and
other
formulas. You can look at those. And the first question you need to
atoms
ask yourself is,
and its
does it contain oxygen? Does it contain oxygen? From here, we're going to branch off either yes or
Each
no.
unpaired valence electron is able to pair up
If
with
it
another
does
single
contain
electron.
oxygen, the situation can be a bit,
When we're
I don't want to say
working with
complicated, but there's
organic
two different
compounds,
choices.
we often use
It
something
will
called
either have an
Maxwell
8
formula.
ion or an
And
8
what these
ion.
are
So you need to look up the
simplified
ion and see what its name is. So for example, if we had HNO3, this is nitrate. So it's an 8 ion. So
And they
this
show the number
would
of
be
atoms in
hydrogen
each organic molecule and the arrangement of those atoms.
nitrate.
So if we
But that's
flip
just its
over, here are
ionic
some
name. That's not
examples
changing it to its
of
acidic
some
name, which is
structural
what you have to do
numbers.
now.
We're
So what you
simplifying
do
these
is you
diagrams,
drop
so each
the
bond
hydrogen
and pair has been replaced by a
from the
line.
name,
So each of these lines represents bonding pair.
and you change the ending from 8 to ic.
And
So
they
it
show
becomes
the
nitric
arrangement of the
acid.
atoms.
If it was an ite ion, like chlorite, so HClO2,
Same down here, and this is spelled out a little bit more with
so this
showing
would
the
have
Lewis
been
diagrams for each of
hydrogen
the individual atoms that are involved, and then showing the structural
chlorite.
formula in which each of the bonded pairs
You
have been
again
replaced by a
drop
line.
the hydrogen
Lone pairs are still
from the name,
left there.
and this time you change ite to us. So this becomes
Organic compounds are
chlorous
classified into some special groups.
chlorous
One
acid.
group is hydrocarbons, and as the name suggests, they contain only hydrogen and carbon. So contain hydrogen and carbon. Alcohols have an
If
OH group.
Something does not contain
and
oxygen. If you went
ethers
down the no
have a
path,
COC
then
group.
it
they
ends in
have an
ide,
oxygen flanked
so
with
like
2 carbons.
HCl,
And we'll look at
hydro-
some examples of this.
hydrogen
today.
chloride. So that would have been hydrogen.
Sources of organic compounds are
Chloride.
naturally occurring sources. And
It
these
instead
are, for
becomes
example,
hydrochloric
organic compounds are produced by plants during
acid.
photosynthesis.
So you keep the
And they also come
hydrogen,
from
change it to
within wood.
hydrochloric acid. When you're naming bases and salts, it follows the same rules that you learned in chapter 7.
Organic compounds can also be synthetic in that they are man-made.